All right, imagine that you're standing and you're holding a lasso, and your lasso has and it's not really a lasso, it's just a rope, and your rope is you got a massive object on it, right? You have a ball, and you're swinging it around, okay, around your head. Okay, I just have it up above your head. It's easier to do it like around your body rather than way up, because you smack yourself in the head if you don't do it right. So, okay, so this thing's traveling in a circle. If you were to just fling it and let it go, okay, how would it travel? Well, so you're spinning it around, and then you just let go of it. Okay, right? It's going to fly off on the tangent, right? It's going to fly off straight, into the page here. It would just fly off straight after you let go of it, because it would eventually land on the ground, because the only force acting on it at that point would be gravity, right? Okay. Well, that means that something has to be keeping it in a circle. Okay, when you don't let it go. And so there has to be some other force that is acting upon it, keeping it in a circle. And whatever these forces are called, okay, these are called centripetal forces. Okay, and this is any force directed Okay, this is any force on an object that is directed towards the center of a circle. That's all it is. Okay, it could be anything as long as it is directed towards the center of a circle. Okay. All right. So in this particular case, if you're spinning it around your head, okay, and it's a horizontal circle, what is keeping your object in the center? What is keeping it in the circle? What other object is keeping it in the circle? It's the rope, right? Okay, and what force do we associate with ropes? It's a tension, right? So in this particular case, we've got our circle here. In fact, I knew I needed one of this for a reason. I have my circle drawer. Okay, and at any given moment, we have this is our rope, and it's pulling on our massive object here, pulling on our ball, using a tension. So in this particular case, the tension the tension is the centripetal force. They can be all kinds of things. Okay, but in this particular case, it is the tension that is the centripetal force. Later on, we're going to get towards charged particles traveling through magnetic fields. And it's going to experience a force that causes it to turn. And it is a centripetal force acting on the particle, even though you don't see anything happening to it. It's just going to go when it travels through. Okay, so this tension then, whatever's keeping it in the circle, if this is the only force acting on it, this tension then is going to equal, along with what other factor you know about with tension, is going to equal our mass times our acceleration, which is our centripetal force, which is mv squared over r. Okay, tension doesn't always equal mv squared over r, but because it is the centripetal force, it equals mv squared over r. In this case, you guys, do we understand that distinction? Okay. we're going to take this and we're going to take it out to an extreme, to the point where he spins it so well in such a huge circle that he is standing with a really long string. Let's make it longer than that. Okay, and he's holding onto this string and spinning around it every time that the Earth completes a rotation. So does the ball. Right? And so he is holding on to the ball with a certain tension that is keeping the ball directly above him, traveling in that circle. Yeah? What's the centripetal force? Right. Well, at this point, it's not just the tension; it's also gravity, right? Okay. So to the point where, if that's traveling fast enough, you don't really need the tension anymore, right? That if this thing's traveling fast enough on its own, it'll just stay out there if it's outside the atmosphere, and it will start orbiting the Earth. Yeah? Okay, so a couple things we need to talk about. We need to talk about if it's orbiting the Earth then, but it's not touching it, then we know that then our centripetal force in this case is our force of gravity, right? But here's the thing. At this distance, regular 9.8 meters per second squared doesn't work anymore, and we need to introduce Newton's fourth law. We don't really call it his fourth law, but it is his fourth law. We introduce Newton's law of universal gravitation. And it is this that allowed us to go to the moon and send things into space and predict where they're going to go and launch them to other planets, like the Cassini probe that just crash landed into Saturn, even though it spent like 5 years around it taking all kinds of amazing pictures. Okay, and it is this, that the force of gravity on any object is equal to G, which is the universal gravitational constant. It is just a value, and I'll give that to you in a minute, times the mass of the two objects that are exerting gravity on each other, divided by the distance between them squared. This is the law of universal gravitation. This is an inverse square law. That two objects that are twice as far apart are going to have 1/4 of the force between them. And so as this number starts to go up, the force starts to decrease exponentially. Yeah? Universal gravitation is always attractive. Okay, that the two massive particles will always attract each other. They will always pull one towards the other. Okay, and we sort of visited this when we did our Newton's third law thought experiment. That when we jump, when you exert a force downward upon the Earth exerts a force upward upon you, right? So when you jump, You're pushing down into the earth, and the earth is pushing upward into you. Okay, and just as you are able to lift yourself off the ground, you're also pushing the earth away from you. Okay, although it doesn't move as much because it's really, really big. Okay, or when you're driving in a car and you hit a bug and it goes on the windshield. Okay, the bug exerted the same amount of force upon the car that the car did on the bug. Just the bug isn't structurally sound enough to handle it. Your car is. Okay, it would be very disappointing if you ran into a bug and the car crumpled rather than the bug. That would be a very bizarre, mighty mosquito. It destroys the car rather than. Okay, so the same thing is happening with gravity. Is that because we are massive objects, we have a gravitational pull. We are pulling the Earth towards us, and it happens to be equal to the force with which the Earth is pulling us towards it. Okay, and it's this value here. Notice it doesn't matter which one of these is which, as long as you just have the two masses. Okay. All right. So this can then be used to determine how fast you need to travel at any particular distance from the Earth in order to stay in orbit. Yeah? And how do we do that? Well, if you're in orbit, and this is your gravitational pull, then this is the only thing keeping you in a circle. And you can use this. This is our centripetal force, and this is our gravitational force. This becomes our centripetal force, and we can solve this. We'll call that us. And that's going to be the mass of the Earth, which is the other one. Okay. And this value right here is how fast you would have to travel at any distance away from the Earth, from the center of the Earth, in order to remain in orbit. This is where, our centripetal force equals our gravity. That make sense? Okay. Right. Or in other words, this is how fast that you have to, say, fire a bullet or launch a projectile so that the rate at which you are falling towards the Earth is equal to the rate at which the Earth is falling away from you. Right? So those two curvatures are the same, and if that continues, then you have this, you have this object that keeps falling towards the center of the Earth, but it never hits it. It's like you couldn't hit water if you fell out of a boat. Well, that's exactly what's going on here. It's that you can't hit the Earth, if you fell off because you're going too fast for it. Okay. We will talk more about the law of universal gravitation. We'll talk about Kepler's laws and how those actually govern planetary motion. But this should be enough for the next few days for your work. And so we'll stop there. I did forget to tell you what G was. So the value of G is equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And this is the value of that constant. And it's because this gives us force, we need newtons in there, and it's meter squared on the bottom with kilogram squareds. We have meter squared here and kilogram squared up here, so we need to cancel those out in that. There's a more, if you were to look it up, you'll have a different units on there that already cancels with, that'll give you other cancellations with meters and kilograms. I think it's It's like meters cubed per kilogram second squared, I think is just the kilogram meter seconds value for it. But it's really just this. Newtons times meters squared per kilogram squared. And that's G.